Hi, I'm Ross Tate from the University of California, San Diego, and I've been helping Red Hat design the type system for their upcoming language, Ceylon. In this talk, I'll be focusing on the various problems we came across early on and showing what our current solutions to those are after considering the various options. First, what is Ceylon? Well, it's object-oriented, it's meant to be industry scale, it's statically typed, and it's managed. So this is much like Java, C#, and Scala. However, it also will have decidable type checking, decidable local type inference, and principal types. And these are specific to Ceylon. And this is really where my contribution comes in. So here's a quick glance at some Ceylon code. As you can see, it looks a lot like Java code, which makes sense because it's predominantly based on Java. There's some differences, but I'm not going to be going over those differences because I'm going to be focusing at the type level. So how did I get involved in this project? Well, in PLDI 2011, I presented a paper where I had found various problems with Java's type system, and I fixed those problems with Java's type system. Now what I do for Ceylon is I find problems with Ceylon's type system, and I fix problems with Ceylon's type system. Fixing problems in a type system often means removing or restricting features in a type system, which has given me a bit of a reputation with Ceylon's development team. This here is Gavin King, most well known for the Hibernate Java database system, and he's leading this project for Red Hat. So some type features that Ceylon has is it has nominal subtyping, so the name integer is a subtype of the name object. We don't look at the structure of it, we look at its name. Declaration side variance, which means that list integer is a subtype of list object because integer is a subtype of object and list is covariant. For us, we use immutable lists, so that's sound. We also have intersection types, so you can say serializable and iterable integer, and this means that's both serializable and it's an iterable of integers. And we also have union types, so you can say double bar string to say that's either double or string, or it could possibly be both, although in Ceylon that won't happen with these specific types. Unfortunately, with just this small list of features, we already have a number of problems, and I'll be going over a few of those problems in this talk. Starting with declaration side variance, subtyping alone is already undecidable, as shown by Candy and Pierce. However, declaration side variance is subsumed by use side variance, which itself is subsumed by wildcards in Java. And I showed at PLDI 2011 that you can impose various restrictions on wildcards for decidability. And so by translating those restrictions to Ceylon, we were able to solve this problem with declaration side variance. Intersection types are a little more interesting. Suppose list has type list foo and list bar. The question is, was the type of list.get 0? Well, you might argue that it's foo, since list foo is a subtype of the intersection, but you could also argue that it's bar, since list bar is a subtype of the intersection. So who's right? Well, one solution would be to infer from context, see whether it's being assigned to a foo or a bar. However, we could assign this to an object, which provides no useful context, so it doesn't solve our problem. C# solution is to reject ambiguity. Say class foo implements both list int and list string. Well, then we can allocate a new foo and try to write foo.get0 out to the console. What will happen though is C# will say, hey, there's an error, this is ambiguous. It's not exactly what happens, but it's the intuition for what goes wrong. This makes sense, but what's weird is that if you instead said list int foo, this code gets accepted. We haven't changed anything besides just what the type of foo is. Particularly, this means that foo is not a true subtype of list int. Foo expressions can't always be used where list int expressions are accepted. This implies that smarter inference can actually increase ambiguity, and so if you make your type checker smarter, it might actually reject more code, which is not what we want. And so we don't use the solution. Our solution is to use a concept which we call principal instantiation inheritance. This says that a class or interface can extend CX and CY only if it extends CT as well, and CT is a subtype of both CX and CY. That is, there is some principal instantiation T which subsumes all the other instantiations. This implies that any instance of list X and list Y will also be an instance of list X and Y, which solves our problem, provided we can incorporate it into the type system. This means we have to change the standard rules for intersection types. The standard rules say that x is a subtype of y and z if x is a subtype of y and x is a subtype of z. Furthermore, x and y is a subtype of x, and x and y is a subtype of y. With our rules, what we do is we keep the same top rule, but for the bottom rule, we instead compute using a simple function the principal instantiation for the intersection. In particular, list A and list B will be a subtype of list A and B, and this solves our original problem. So now moving on to union types, here's an example usage where we take something that we know is either a string or an integer and we cast it to each of those two cases. There's no more cases necessary since we have a bounded union here. And so we have a completely type-safe way of doing casting. On a related note, Ceylon also has explicit null types. So given an array of strings, if you access the fifth index, it returns a string question mark, indicating that it's either a string or it's null. This means we have no index out of bounds exceptions in Ceylon. To extract that string, if it is present, you use this construct where it says if exists some string that's equal to strings 5, then we can say print that string. This means we also don't have any null pointer exceptions in Ceylon. One might try to represent null types as using unions. So for example, you'd say x question mark is shorthand for x or nothing, where nothing is a type that only has null as its inhabitant. Exist then is a shorthand for casting to is x. The advantage of this is that x is a subtype of x question mark. So you can write null hello world and it'll figure out that this is an array of string question marks. Unfortunately, this doesn't work. The reason is because of doubly-null types. Say I have some string question mark array, null, hello, and world. And for each index I look to see whether an index is valid or not. So what happens if I check at index 0? Well, it's a valid index, so we'd expect exists to return true. But then what happens if I is 3? Well, then it's not a valid index, and it returns null, just like when I was 0. And so now, is that valid or is that invalid? And the problem is you can't distinguish these two cases in any way if ever you have x to be a subtype of x question mark. So we had to change our type system to use specifically disjoint unions, meaning the two cases can never overlap. So for nulls, what we did is we made a class nulled, which has two subclasses, null, and it exists, and nothing can be a subclass of both. The of clause indicates that those are the only two subclasses of nulls. That way we know that those are all the cases possible. Unfortunately, the solution means that we had to sacrifice a feature. X is no longer a subtype of x question mark. However, I've proven that there's no way of getting around that problem if we want the prior examples to work. And so this is the solution that we're using. Now, type argument inference is a whole other problem, and it's important because we want to encourage people to write generic code. Here's a generic method which constructs a singleton array for any class T. However, T is not inferable because array is invariant. To see why, singleton array hello could have the type either array string or array object, and because array is invariant, neither one is better. Particularly, this means that there's no principal type for this expression. On the other hand, if you were to construct a singleton list T, T is inferable because list is covariant. Singleton list hello could be a list string or a list object, but list string is a subtype of list object, so the principal type for this expression is list string. So Smith and Cartwright showed that you can solve this problem, at least partially, by incorporating unions and intersections in the type system, and we already have those. So we've adopted their algorithm, but made a few fixes and specializations towards Ceylon. Thus, if you make the generic method if then else, which takes 2 t's and returns 1 t, and you give it hello and 5, we'll figure out that the principal type is string or integer. On the other hand, if you write some generic method max, which takes a number of t's, and you give it no t's whatsoever, we'll figure out it has type bottom, which is a subtype of everything. Then we'll use intersections in the special case where there's some contravariance in the situation, although that's not common, and we'll use top in those same situations when there's just no cases provided. Now, constraints on type parameters make the problem even more intricate. What's interesting is sometimes constraints can help you and sometimes constraints can hurt you. For example, with this generic method foo, normally we wouldn't be able to infer the type for y. But because of the constraint on x, y's type is actually uniquely determined by x's principal instantiation of invariant, and so foo's type will always be inferable. However, for this case, less than's type normally we'd be able to infer the type top for t, but because of the constraint on t, we will never actually be able to infer the type for t, no matter what type you give it. So the problem is that there are going to be type parameters which will always be inferable, and there are going to be type parameters which will never be inferable. And we don't want the uninferable type parameters to drag down the inferable type parameters. Our solution then is to allow the user to separate the two groups of type parameters. So when you declare a function, you give the list of explicit type parameters and the list of implicit type parameters. And the cool thing is we will tell you right then and there whether or not the implicit type parameters are always inferable. So there's no more guessing like there is in C#, Java, or Scala. Then when you actually call the function, you only have to give the explicit type arguments, and we'll be able to infer the implicit ones from the function arguments you give it. If you happen to use the function in a higher order way, then you have to pass the implicit type parameters as well, because we don't have the arguments of the function to infer them from. So using this technique and this syntax, we will always be able to give a principal type to function invocations, even with type argument inference. In conclusion, from a researcher's perspective, type theory for a practical language is surprisingly difficult. There are many language features to consider, and more importantly, each language feature you add on may clash with prior language features, so you have to consider them all together rather than view each one independently. Furthermore, there are many more language features that we're still considering, so you have to make sure all the existing language features are forwards compatible with all language features you might add. Also, what I've shown in this talk is still tentative, since Ceylon is still under development. So thank you for your attention, and feel free to contact us about any questions you may have.